Time Series is a new resource of BigML, and it's also kind of a new way about thinking about your data. So I'm going to start with kind of a conceptual level of how time series is different from our other existing machine learning tasks. So with your normal machine learning task, classification, regression, trees, and ensembles, the task is to discover some kind of pattern within your data. So here on your left, we have a toy data set. Each row is an entry containing the color, the mass, and the kind of thing. If we just take a glance over the rows, we can pick out some kind of patterns like, oh, if the color is red, then the mass will be less than 100. If it's a pineapple, then it's not going to be blue. Or if it is blue, then it's going to be a 10. With your normal machine learning data sets, if you rearrange the rows, then that pattern is still preserved. You can still see all the same patterns that we just called out. This is because each row is considered to be a standalone instance of that pattern. In contrast, when we are learning time series data, we're looking at the data kind of in a more holistic sense, kind of how it evolves from the beginning of the data set to the end. So if you look at this series here, pineapple harvests, we can pick out some patterns like it has an exponential shape growth. And on top of the exponential trend, we see some error, maybe plus or minus 50 tons. And what happens is, if you rearrange your data, unlike with our machine learning data, then we lose any information about that pattern. It's disrupted. Now, the next half of machine learning is doing forecasts or predictions. And this is extrapolating your learned patterns to novel inputs. So if we have a decision tree here and we say, okay, now I have something that's red and its mass is 11. It's not something that was in your original data set. Can you tell me what it's going to be? And it comes back and says, okay, it's an apple, and also gives you a measure of how certain it is about that prediction. In this case, it's 34%. With time series, it's pretty analogous, but this time the novel input is the future. It's a period of time beyond the data that you use to train your time series model. So we say around 200 time index, what's this time series going to do, right? And so we get a prediction, that's the solid line. And we also get a measure of uncertainty too, a band around that prediction, which we are fairly certain the actual value is going to lie. One more difference between machine learning tasks and time series tasks is when you go to do evaluations. The evaluation workflow, as you might know, is you hold out some of your original data, you train on what's left, and then you run your model on what you held out, and you compare what the model gives you to the true values. So with trees or ensembles, you would just take a random sample of the rows and hold those out, because each row is independent. It's as long as they're still representative of the underlying pattern, it doesn't really matter which ones you pick. On the other hand, with time series models, because the predictions are by definition in the future, you need to hold out the final rows in your data set, and that's what we call a linear split here. That's enough about conceptual differences. I'm going to go into some detail into the exact kind of time series modeling that BigML does. We use a method that's called exponential smoothing. So I'm going to concentrate on that smoothing part I named for now. So the idea behind smoothing is you have some kind of signal, some kind of time series that has a signal that you want to recover, but it is kind of corrupted by noise. So this is a picture of the closing prices of the eBay stock symbol. And you see it has some shape here, but it also has a lot of fuzz that could be distracting from the story you want to tell. One way you could get rid of that is by doing a moving average. At every time index, you would look at a window. In this example, we're using a window of 11 points. And so you would take all the points in that window around a particular time instance, and you would weight them equally, and you would sum them. You're basically taking an arithmetic mean. After you do that over the entire data set, you would get this blue line here. So you see it only contains the large scale movements of the stock price, and most of that noise has been smoothed out. So that's a moving average filter, but what we're doing is exponential smoothing. And the way that's different is at each time index, we actually look at all the data from that time index back to the beginning, but we weight the ones closest to the present most heavily, and decrease the weight exponentially going back into the past. And again, you see if you do this, you get a smoothing effect. You only see the big scale movements of the stock price, and all the noise has been filtered out. So what is there to recommend exponential smoothing over a simpler method like moving average? With a moving average, you're summing over a fixed width window. You're basically disregarding anything that's outside of that window. And with exponential smoothing, you're considering the entire history up to that point. So you're giving that historical data some chance to still influence your current state. With moving average, all the points that you are considering are uniformly weighted, whereas with exponential smoothing, we consider the data closest to the present we give the most weight to that, and so it has the most influence on the filtered result. And that kind of intuitively makes sense, like the things that are closest to now should matter more than things that happened far in the past. As far as parameters, moving average has one parameter. It's an integer parameter that controls that window size. And exponential smoothing has two parameters, and they are continuous floating point type parameters. That's an initial state and a smoothing coefficient. The consequence of having these continuously valued parameters is it's more possible to it's possible to more finely tune the smoothing fit to your data, and you can possibly get better results than moving average. The additional benefit is because exponential smoothing is kind of a recursive type relationship, you can build what's called a state space model, and that allows us to estimate error, and that gives us the possibility of computing forecast intervals when we do our predictions. Lastly, this smoothing methodology can be extended to more components of a time series, namely trend and seasonality, and I'll get into what those are right now. So trend is defined as the difference between two consecutive levels in your time series. And that's a little vague because there's two ways you can interpret that. One way you can say, okay, if I take just the difference, if I subtract one level from the last, then that's what's called an additive trend. And when you model a time series that way, you end up with kind of a linear shape like this. On the other hand, if you define it as the ratio between two consecutive levels, then you end up with what's called a multiplicative trend, and your growth looks more exponential or geometric like that. Again, we do the same exponential smoothing procedure with the trend like we did with the level, and it's dependent on an additional parameter beta. The last thing about trend is if you don't do anything special, then when you forecast a model of a trend, then it just extends that trend out to infinity. And if you are doing a really long-term forecast, that might not be realistic. So what we can do is we can apply some damping. This is an additional parameter that lets the trend kind of level out after a long period of time. And you can do this with both multiplicative and additive trends. The next component for time series we're going to look at is seasonality. Seasonality is recurring pattern of variation that occurs over and over periods of consistent length. So for example, if you have some data that's monthly air conditioning sales, you would expect this data to have higher values in the summer months and lower values in the winter months. And so we would call this a seasonal pattern with a period of 12 data points because there are 12 months in 1 year. Another example could be vehicle traffic in some downtown commercial district. You expect traffic to be higher during the work week and lower during the weekend, Saturday and Sunday. This would be a seasonal pattern with a period of 7 data points. And seasonality may be present in time series with or without trend. And likewise, trend can be present with or without seasonality. We apply the same exponential smoothing procedure with its own smoothing coefficient, gamma. Seasonality also comes in two flavors, additive and multiplicative. With additive seasonality, we consider the seasonal variation to be independent of the level of the time series. So you can see here in this example, here where the level is low and here where the level of the series is high, the amount of seasonal variation is pretty constant. Whereas with multiplicative seasonality, we consider it to be proportional to the level of the time series. So down here, we have a lower amount of seasonal variation, and up here, the seasonal swings are noticeably higher. The last component of time series that we're going to talk about is the error, and this is any kind of variation in the time series that is not accounted for by your trend or your seasonality model. And with most real-world data, you're going to have some error. You might be noticing a pattern here, but error also comes in additive and multiplicative kinds. And again, it's just defined on whether or not it is proportional to the level of the time series. The choice between additive and multiplicative mostly affects the kinds of forecast intervals you'll get when you're using your time series models to predict. With all these components in time series, we have a lot of options on how to combine them. And that means there's a lot of different types of exponential smoothing models. So we come up with a bit of a shorthand to refer to any specific combination. We use this 3-character nickname, where the first character is the kind of error, the second character is the kind of trend, and the third character is the kind of seasonality. So we put it all together, and we can build this table of all the different possible combinations. So different combinations of seasonality up here, different kinds of trend, and for each combination of trend and seasonality, we have an additive type and a multiplicative type for the error. Now, a number of these model types are considered to be unstable numerically, so BigML does not try to fit them. And there's an additional requirement that if you want to fit a multiplicative error model, then your data has to be strictly positive. Potentially, you are trying to decide between 19 different model types. So how do you know which one to go with? Well, you don't have to know, because BigML will decide for you. By default, we fit all the different model types to your data, and then we rank them with a number of metrics. The first 3 here on the left are called information criteria, and then we also do an R-squared. The 3 information criteria, they all are trying to accomplish the same thing. They're trying to assign a score based on, first, how well the model fits your training data, but then it penalizes that by how complex the model is, because the idea is with more model complexity, you're running into a greater chance to overfit, and that's not a good thing for being able to generalize to forecasts. And so very broadly, the AIC is kind of your default information criteria, and then the bias corrected AIC and Bayesian information criteria, they penalize extra complexity a little heavier than the AIC. There's a lot of discussion in stats literature and community about which one to use and when. For most instances, AIC should be fine. The last one is R-squared. R-squared is purely how well the model fits to your data, and so you're not concerned at all of how complex your model is. So if you go with R-squared, then you are running the risk of choosing an overfit model. So let's take a step back and see how to use time series in BigML. If you use BigML before, this workflow should be pretty familiar to you. First, we bring in our data and as some kind of plain text format as a source, and then we create a data set from that source where we serialize and create field summaries. Once we have that data set, we may do a training and a test split if we are planning to do evaluations. And again, this training and test split for time series is going to be that linear split that I talked about earlier. So from your training data set, you would then train your time series model. And one thing that's different here about time series models compared to other BigML models is that we bundle them together with a forecast already. This is because, say, when you're building a decision tree, you don't know what the user is going to want to predict it with, what kind of input the user is going to want to give to make predictions. But when you train a time series model, you are by definition going to want to predict out to some point in the future. So what we do is we pick a medium length horizon, 50 time indexes, and we automatically give you a forecast up to that horizon. If you want to go longer than that, then you can take your model and you can request a forecast with a longer horizon. So once you have your model in hand, you can evaluate it if you've done your training and test split. And that is conceptually the same as other supervised learning evaluations, where you are comparing the forecast against the ground truth, computing error metrics out of that. So with that, I'm going to dive into the demo. Our first demo is using data from NASA's battery prognostics experiment. What they did here is they took a bunch of lithium-ion rechargeable batteries and they just charged and discharged them over and over again. With each discharge, they measured what the actual capacity was. Let's get out of here and let's look at the data. The data contains 2 fields. One is just a numeric field that counts up, that's just the number of charge discharge cycles. And then the second field is another numeric field that measures the actual capacity of the battery. So I'm gonna load that into BigML here. I have my data stored on Google Drive. So you can see it's detected two fields, two numeric fields. This is what we expect. This is your chance to change any data types if you got it wrong, but it looks good to me. So I'm going to go ahead and do a one-click data set. And here we've generated some statistics for each field. And serialize the whole thing. And I'm going to go ahead and build a time series model using just our default parameters to see what we get. Okay, so on the top here, you see that with our default options for time series, we search among all different types of exponential smoothing models, so all error types, all trend types, all damping types, all seasonality types, and we automatically we try to automatically detect if there's any seasonal period to it. Here in the plot, you see our best model that was selected, ranked by AIC. The black line is the original data, and the purple line is the model's fit to that data. And the way that this fit is generated is as we are building the model, we do a one step ahead forecast at each point, and we compare, and that gives us the purple line. And we can quantify the quality of fit by how far the purple lines and the black line is. So our question was, when will the battery capacity drop below a certain point? So at the end of our training data here, we're about 1.3, and let's say maybe we want to see when it'll drop down to 1.25 amp hours. So we'll slide out our forecast here. So the solid line here is what's called the point forecast. This is the forecast you would get from the model if you did not consider any of the error characteristics of the model. And then the shaded region around the point forecast is called a forecast interval. And this is for each time point, this is the band in which we are 95% sure that your forecast will exist. And the width of that band depends on the error characteristics of how we fitted the model. So our question was 1.25 amp hours. So if we look on the right side and we slide out towards the right, we can see at 193 cycles, our point forecast is at 1.25. But if we wanted to be a little more conservative, we can actually look at the lower bound here and see where that crosses 1.25. And that looks like around 175 cycles. So if our question was how much longer can we use this battery, we could say at least up to 175 cycles, and probably don't want to go above 190 cycles before it has too little capacity to be used. Okay, so that was our quick example. I'm going to go into a second demo that's a little more involved. Next demo is kind of a more traditional forecasting task. It's forecasting production, and the data we're using comes from Eurostat. It's a data set that contains the monthly milk production of cow's milk in Croatia between the years 2000 and 2008. And let's see what that looks like real quick. So again, it's two fields. On the left here, we have a date stamp, and then we have the production of cow's milk for that month in thousands of tons. So we'll go ahead and load this one into BigML. Okay, so even though there are only two fields in our data set, the date and the actual milk data, what BigML does when it detects a date stamp field is it actually breaks it out into its components. So we have an automatically generated field for the year, the month, the day and month, and the day of the week. And we'll use some of those in a bit. So remember that. So let's go ahead and create our data set. Okay, so we created our data set, and we want to look at what the data looks like. So here's a time series model I pre-built, and this is just showing the underlying data. So you can see there's a clear seasonal pattern, but it's not very smooth. It's got a lot of jaggies, but they are oddly consistent, and it doesn't really make sense if you think about it that cows would have this kind of very fine grained variation. So what could be going on here? Well, this data set, it might be in need of what's called a calendar adjustment. When you have data that's the sum of something per month, you could see some variation that's not due to any change in the actual quantity you're interested in, but it could be due to the fact that the different months of the year have different numbers of days. So, for example, in February, with the fewest number of days in the month, there are fewer days to sum up that value, and so you will get an artificially lower value. That's not due to any change in the rate of which that value is produced. So in our example, if we have pounds per month of milk, the easy way to correct that is just to divide each value by the number of days in the corresponding month. So pounds per month divided by days per month gives you pounds per day, and that's something that was more consistent to month. So to do that, we're going to use a WhizzML script. WhizzML is a domain-specific language that's used to automate BigML workflows. It's you can do a whole lot of stuff with this, and calendar adjustment is a relatively simple task. So we're actually showcasing WhizzML, and we're also showcasing Flatline. Flatline is another DSL for BigML that goes row by row and performs data transformations. So what we're doing is we're going row by row. We're looking at the month of that row and the data value of that row. And depending on a month, we're dividing the data by the appropriate number of days. And what the WhizzML script is doing is we are just wrapping that transformation in a way that we can select the names of the fields that we're going to use. So let us choose our milk data set and execute it. And we can go back to some TV magic here, and we'll look at the result. Okay, so now you see this is the extended data set created by our WhizzML script. We have a new field here called daily milk. And what the question now we want to ask is, well, did this calendar adjustment actually help us at all? So what we're going to do is we're going to go into a little more details of the options with our time series models. So we're comparing, we want to compare two different time series. So we're going to add our monthly milk and our daily milk as the objectives. Time series is the first model type in BigML where you can select multiple objectives. We're going to go into our advanced options here. So this tab is where you can restrict the kinds of exponential smoothing models that we search for. You don't have to do this, but it does kind of restrict the number of things you need to think about. So we know that this is seasonal data. So I'm going to say, okay, let's only consider models with multiplicative seasonality. We know that the period should be 12. So if we wanted, we could manually set it here, but I'm going to let BigML go ahead and detect it automatically still. The next option here is where you define the date range of your data. So I know that the data starts at January 2000. And I know that between every data point is 1 month. So this is purely a cosmetic option. It just makes sure, it just lets you have the correct x-axis values on all the plots. So those are all the options I want, and I'll go ahead and create it. And I'll switch to the model that I've already built. So right off the bat, you can see that the shape of the calendar adjusted data is quite a lot smoother than the unadjusted data. There's a lot fewer jaggedy bits. We can see here that we only looked for models with multiplicative seasonality, like we had specified. And it did in fact detect seasonal models because that's all we have here. So the best model if we rank along AIC, is a model with multiplicative error, additive trend, and multiplicative seasonality. But if this actually changes, if we go up to the BIC selects no trend as the best model. Again, this is because the BIC penalizes model complexity more heavier than the AIC. So without a trend, you have a simpler model, even though the fit is worse, it's not worse enough for the BIC not to prefer it. Another way we can see the difference between these is we look at the forecasts. Let's turn off the intervals so you can see it more clearly. You can see the difference. This is a real difference that you get depending on which scoring metric you use, because with no trend, the forecast is pretty flat, and with a trend, it grows up and up. BigML also provides a few simple forecasting methods to let you compare the model forecast against. So a naive forecast just takes the last value of the training set and just repeats it out to infinity. In case of seasonal models, it takes the last seasonal period and repeats it out. The mean model is quite analogous, but instead of taking the very last seasonal period, we're taking the average seasonal period and just repeating that out forever. And then the drift-based model just takes the first point in your data set and the last point in your data set, draws a straight line and extends it out like that. So you can use these as kind of a sanity check to see if you should be skeptical of your time series model results or anything. You know, if they're really close to the naive forecast, you might think something's up. So let's go back to our original question and let's compare our calendar adjusted data, our daily milk field, with our monthly milk. So let's look at the information criteria score here, minus 132, and with information criteria, lower is better. So, and we go to our unadjusted data and we see that the score is 386. So you might think that that automatically means that our calendar adjusted time series is better. But the thing you need to be careful with for these information criteria is they are data dependent. The number you get here depends on the scale of the data. Since the calendar adjusted data is going to be less by about a factor of 10 or 30 actually, then you will naturally see lower information criteria scores from the adjusted data. So because these scores are depending on the scale of the data, you can really only use them to compare models that were built using the same data. So if that's the case, how are we going to compare our two time series? Well, let's go back to our data set. And we're going to want to do an evaluation. So we want to do that linear split where we lop off the last 20% of rows. Then we're going to take our model and we're going to evaluate with that last 20% there. So I have that result here. So when we do our evaluation, we are taking that test data, which is the black line in the shaded region, and we're computing the difference between that and the forecast values we get from the model in the same region. So basically, again, the difference between the black and the colored line here. There are a number of metrics we can use to compare our models. We have mean absolute error, mean squared error. These are kind of your straightforward comparing two values kinds of metrics. And then we have a number of metrics that are used pretty more frequently in the time series and forecasting communities. The symmetric mean absolute percentage error expresses the difference as a percent. I like the mean absolute squared error, mean absolute scaled error, sorry, for a couple of reasons. One, it penalizes positive and negative errors equally. And two, it is invariant to the scale of the forecast. So if you are looking at errors in a large when you're forecasting large values and errors when you're forecasting small values, the error metric does not change. And this is going to be good for us because we are comparing two time series on different scales. So the daily milk here has around 2, and the monthly milk, the unadjusted data, has values around like 30 and 40. So let's pay attention to our best mean absolute scale error here. It's about less than 0.4. And we'll switch to the evaluation results from our monthly milk data, our unadjusted data. And we'll see that the value is above 0.4. So the takeaway here is the calendar adjustment not only makes your data look more smooth, it takes out a lot of distracting details from the story you want to tell, but it also can, in some cases, improve the performance of your model. So it's definitely something that's worth trying when you have data that's susceptible to calendar influences. So BigML brings time series analysis using an industry standard exponential smoothing methodology. And you can do all that with your familiar BigML workflow from source to dataset to model and then forecast and evaluations. You get all that with BigML's market-leading visualization and collaboration features that you might be familiar with from our previous models, like models ensembles. You don't have to do any kind of special data preparation for time series. You can train a time series on any numeric field. And BigML's time series saves you time in that you can fit multiple fields at once, and you can explore the entire family of exponential smoothing models in parallel with one model creation. And another time-saving feature is with your time series model, we bundle together a medium horizon forecast, so you can immediately see some results. Lastly, time series models are fully integrated with BigML's WhizzML workflow automation language, as well as our API bindings, such as in Python and Node.js. That wraps it up for the webinar. If you want to learn more about BigML and time series, I encourage you to go to our release page where you'll find all these resources, documentation on the dashboard and the API, as well as some in-depth blog posts that go into more detail about many of the points that I covered today.